I am going to remind you about a few things from field theory, alright. So recall from field theory. So if you have L over K, a field extension, you take a field extension L over K, okay. Then we say when an element of L over K is algebraic, okay, when an element of L is an algebraic element over K, it's an element of capital L is said to be algebraic over capital K if it satisfies a polynomial, a non-trivial polynomial with K, capital K coefficients in one variable, okay. So and if every element of L satisfies such a polynomial over K, okay, then we say L over K is an algebraic extension, okay, that is every element of L is algebraic over K, alright. And if you have elements of L which do not satisfy any polynomial, any such polynomial with coefficients in K, we call such elements as transcendental elements, okay. And if L over K is a finite extension, in the sense that if you treat L as a vector space over K, if the dimension of L as a vector space over K is finite, then a finite extension is always algebraic, alright. And in fact but of course an algebraic extension need not be finite, okay. Now you see if L over K is not algebraic, then it has transcendental elements, okay. There are elements which are non-algebraic, okay, and then given a set of transcendental elements, you can define when that set is algebraically independent over K, okay, and this is analogous to the definition of linear independence over K. So a set of elements of a vector space is said to be linearly independent if no finite subset of that set satisfies a non-trivial linear relation
with coefficients in k, okay. So in the same way a set of elements of L which is said to be algebraic or is said to be algebraically independent over capital K if any finite subset of that set does not satisfy any polynomial relation with coefficients in K. So if you give me finitely many elements of capital L, okay, then those finitely many elements are said to be algebraically independent over capital K if those finitely many elements are not zeros of some polynomial over K in those finitely many variables, in as many finitely many variables, okay, a non-trivial, they should not be, they should, that element, that tuple of elements should not be 0, okay, of a polynomial in as many variables with K coefficients, right. That is when you say those elements are algebraically independent, and this is when you take a finite set of elements and an infinite set of elements is said to be algebraically independent if every finite subset of that infinite set is algebraically independent, okay. And then there is this just like in the case of a vector space you define the dimension as the max, it is a cardinality of a maximal set of linearly independent elements, okay. In the same way if you have a field extension which is not algebraic, then you can define its so called transcendence degree, okay, its degree of transcendence, okay, to be the cardinality of a maximal algebraically independent set, okay. So if there are elements L which are not algebraic over K, you can try to, they are transcendental elements, okay, and then you try to take try to find a maximal subset of these such elements which are algebraically independent, okay, and that cardinality will always be the same, okay. Any two just like if you take any two bases of a vector space are bijective, okay. In the same way any two sets of maximally any two maximal sets of algebraically independent elements will be bijective, and that, and the cardinality of that set is called the transcendence degree of L over K, okay. And we say that L over K has a we say that L over K has a separating transcendence base, okay, if you can find it you can find a set of elements which forms a transcendence basis, okay. A transcendence basis is just given by a maximal set of algebraically independent elements, okay. If you can find a transcendental basis, transcendence basis, okay, such that L over the field adjoint to K given by those given by the transcendence basis is a finite algebraic extension, okay. So there is you want a picture like this, so L, so you have K, okay, and in L you have this family of elements alpha j where j is in some indexing set j, capital J, alright. Then you have the field generated by these alpha j's, okay. So this is a transcendence basis, and the transcendence basis is it is just a it is just the analog of a basis, alright. So it consists of a maximal subset of algebraically independent elements. A usual basis will consist of a maximal subset of linearly independent elements, a transcendence basis will consist of a maximal set of algebraically independent elements, okay. So you want a situation where you can find a transcendence basis, okay, and you want this extension to be finite separable, okay. So you want I mean this is the best thing that can happen with a field extension. The best thing that can happen with a field extension is that the field extension splits up into two extensions like this. The first one is given, we said that this extension is a purely transcendental extension, okay, because it is the extension which contains only, it is gotten by simply adjoining all the transcendental elements from all the elements of a transcendence basis, okay, and then this over this will only be a finite extension. This will be algebraic, okay, because there won't be already this contains a maximal set of algebraically independent elements, okay. This over this cannot be transcendental, because if there is an element of this which is transcendental over this, then I can take that element and add it to this to get a bigger transcendence basis, and that is not possible. So this over this has to be algebraic, okay, and the fact is that you can make, it would be nice if this is a finite separable extension, okay, and that always happens if the field capital K is algebraically closed, okay. So all this happens if K is algebraically closed, well in fact it happens even under a more weaker condition. It happens if capital K is what is called a perfect field, alright, and but let us not worry about it, alright. Basically what the definition of a perfect field is that if a field is of characteristic 0 it is called perfect, and if it is of characteristic P it is called perfect if you can always find Pth roots, okay. If you take K power P you should get K, okay, and you should be able to find Pth roots for all your elements, right. So an algebraically closed field is always a perfect field, because finding Pth roots is just amounting to solve equations, and over an algebraically closed field you can always solve equations, because that is the definition of algebraically closed. Therefore an algebraically closed field is always perfect, and for a perfect field you have this very beautiful situation. Of course it is important that I need a finite separable extension here, alright, and this part will be a purely transcendental extension, okay, and this is some field theory, alright, but the important thing is that we want to apply it when capital K is small k, our algebraically closed field, and when L is the function field of a variety, okay. So applies if capital K is small k. For us small k is the algebraically closed field over which we are doing algebraic geometry, that is the field over which we are studying varieties, and capital L is the function field of x for a variety x over k, okay. So this is our application, right. So in all these things our viewpoint is that this small k, this capital K is our small k, and this L is the function field of a variety, and then the theorem is that the function field of the variety is a finite separable extension of a purely transcendental extension of K, and you know that if L is Kx, then the transcendence degree of Kx will over small k will give you the dimension of the variety. Therefore but you know the transcendental degree will be just the cardinality of this J, because the transcendence degree is just the size or the cardinality of a transcendence basis. So you know if the variety X has dimension R, then this J will have R elements. So this will just be this will be small k and this will be small k adjoined with R indeterminates or R transcendental elements, alright. So so the picture will look like this. You will get small k and then you will have small k of x1 etc xr, okay, and then you will have L of L which is actually kx. I do not have to use L, so let me just, and this part will be finite separable. Okay, this is the picture that we need. If you take the function field of any variety x, then that function field, what kind of an extension is it of k, you can break it up into two pieces. The first piece is a purely transcendental extension, okay, it is an extension which is gotten by simply adding as many variables as the dimension of x, okay. So this part will correspond, will contribute to the transcendence degree. This will give you the transcendence degree as R, and this part will not have any transcendence. This will, because all the because x1 through xr are already a maximal set of algebraically independent elements. So this over this will be algebraic, and not only algebraic, it will actually be finite, okay, and of course a finite extension is always algebraic, and not only that, it will actually be a separable extension, okay, and the separability is a technical condition, and it is very important, and the reason why it is important, for example in field theory, is that whenever you have a finite separable extension, that can always be generated by adjoining a single element, and that is called the so called theorem of the primitive element. The theorem of the primitive element says that whenever you have a field extension which is finite and separable, then the bigger extension can be gotten by adjoining a single element to the smaller field, okay. So this finite separable extension actually tells you that this k of x is this small k x1 etc xr comma y. You can find a capital Y in kx, okay, such that you adjoin this capital Y to this field, you get this field, and that is all of capital Kx, alright. So the so this you get this capital Y because of the fact that this over this is finite separable, and you are using the so called theorem of the primitive element, which says that a finite separable extension can be gotten by adjoining just one element, alright. And in fact the you see in the theorem of the primitive element says more. It says that if you take a set of finitely many generators for this, okay, then that primitive element is even a linear combination of those generators with coefficients coming from the smaller field, okay. So so the moral of the story is that you have very nice description in terms of fields if you are working with a variety, alright. I mean if you are working with a function field of a variety, right. Now you see now what I want to you to understand is that, well, you see, you take now you take x to be you take x to be a variety over k, alright. Suppose the dimension of x is small r, alright, and you take kx, its field of rational functions, then you can find, of course, x1 through xr, which you can think of as r algebraically independent rational functions on x, okay. So capital X1 through capital Xr are r algebraically independent rational functions on x, okay. And then if you take the subfield generated by these r independent algebraically independent rational functions, you get this field, alright, and then kx over that is a finite separable extension therefore by the theorem of the primitive element you can get this from this by adjoining a single element y, which is yet another rational function on x, okay. And the point is that this y is actually belonging to kx, okay, and kx over this intermediate field is finite, so it is algebraic. So in fact y satisfies a polynomial with coefficients here, okay, y satisfies a polynomial with coefficients here, and the moral of the story is that y, if you clear denominators, y will satisfy a polynomial with coefficients in the polynomial ring in R variables. You can have that polynomial to be an irreducible polynomial, okay, alright, and therefore that polynomial in an affine space with so many variables, its 0 set will give a hypersurface, and that hypersurface, its function field will exactly be this, okay. So this argument tells you that the function field of x, okay, is the same as the function field of a hypersurface in R+1 dimensional affine space where R is a dimension of x, okay. And we have already seen last lecture that I think last lecture or maybe a couple of lectures ago, that if two varieties have the same function fields then they are birational. So all this argument tells you together that any variety x of dimension r is birational to a hypersurface in affine R+1 space, okay. So let me write that down. See y is gotten from the primitive element theorem, okay, and in fact since k of x is finite over k of x1 etc xr and y is in kx, we have y algebraic over k of x1 etc xr, okay. So y satisfies a polynomial, an irreducible polynomial, it satisfies an irreducible polynomial in one variable over kx1 etc xr, okay. But what are the elements of k round bracket x1 etc xr? They are actually quotients of polynomials in those R variables, okay. When you put square brackets it is the polynomial ring in R variables, but when you put round brackets you are going to its quotient field, okay. So y satisfies an irreducible polynomial in one variable, okay, and in fact if you take the degree of that polynomial, that degree will be the same as the degree of this finite extension, okay. For any finite extension generated by a single element, the degree of the finite extension is the same as the degree of the minimal polynomial of that element, and that the minimal polynomial of that element is the unique irreducible polynomial that that element satisfies. It is the polynomial of least degree that that element satisfies. Okay. So here I am looking at the minimal polynomial of y, okay, over this extension, right, and so now, but now the coefficients of this, if in fact you can even make that polynomial monic, okay, if you want, but the point is that's because the leading term can always be made 1 by dividing, okay, by its coefficient, but the fact is that if you think of these as quotients of polynomials in R variables and you clear denominators, what you will get is that you will get that y satisfies a polynomial in R plus 1 variables, okay. If you clear by clearing denominators, y satisfies a polynomial, an irreducible polynomial, in R plus 1 variables, okay. So so what you are doing is y satisfies an irreducible polynomial in one variable, call that one variable as S, okay, and the coefficients are all here, okay, and but the coefficients are therefore quotients of polynomials in the exercise, alright. If you clear denominators, finally and you rewrite, instead of the exercise you put the t's, okay, you will get a irreducible polynomial in R plus 1 variables, okay, which the whole tuple x1 through xr up to y satisfies, right. And now see the, but this is a polynomial, it is an irreducible polynomial in n, so I should not put n here, it should be R, sorry, this should be R. So this is an irreducible polynomial in R plus 1 variables. What is its 0 set? It is a hypersurface in AR plus 1, okay. So the 0 set of f of t1 etc tr comma s, this is a hypersurface in AR plus 1. We have already seen this, a hypersurface in affine space is simply given by the 0 set of a single irreducible polynomial. A hypersurface is by definition a codimension 1 subvariety, an irreducible closed subset of dimension 1 less than the dimension of the affine space, okay. So this is a hypersurface in AR, okay, and for this hypersurface, okay, what is the function field? The function field will precisely be kx, okay. This hypersurface, the function field of this hypersurface, how do you get it? What you will have to do is you have to first get its affine coordinate ring, which is gotten by taking this polynomial ring in R plus 1 variables, and you have to divide by f, okay, you have to divide by f because that is the ideal of the hypersurface. The ideal of the hypersurface is generated by f, so you have to divide by the ideal generated by f, and then you will get the affine coordinate ring of the hypersurface, and then you have to take its quotient field, alright. But then if you divide by f, the moment you divide by f and then invert everything, you will get back kx, because that is how f was gotten, So what you will get is that the function field of this hypersurface is kx by definition. The function field of this hypersurface is exactly kx, okay, because it will be the polynomial ring in these r plus 1 variables. You divide by the ideal generated by f, okay, and then you will get a finitely, you will get an integral domain, you take its quotient field, okay. So essentially what you are doing is you're inverting everything except that you are inverting, it's like taking the quotient field of the polynomial ring in these r plus 1 variables, but putting the additional condition that this f of this is equal to 0, but putting the condition that f of that is equal to 0 will give you the smaller field, okay, which is kx, right, by construction. But so the moral of the story is that now the function field of the hypersurface is the same as the function field of x. Now we have already seen that if two varieties have the same function field then they are birational. So this implies that x is birational to this hypersurface. Okay, so x is birational to this hypersurface. So what this tells you is that, I mean, the whole purpose of my recalling all this, though I did it very quickly and on your part this will demand some more reading, okay, is just to tell you that if you have a variety of dimension r, then it is birational to a hypersurface in a r plus 1. So this is a fact that I need to use. I am going to use the fact that given a variety of dimension r, it is having an open set which is isomorphic to an open subset of a hypersurface in r plus 1 dimensional affine space. So roughly what I am saying is the following thing. I am saying take a variety of dimension r, there is an open set where the open set looks like the 0 set given by a single equation in an affine space of dimension 1 more. The variety has x has dimension r, okay, you take an affine space of dimension 1 more which is ar plus 1, and there is a hypersurface there and an open subset of the hypersurface which looks like the open subset of your variety. So I am just saying that given a variety of dimension r, there is an open set which looks like the 0 set of a single equation in a affine space of dimension 1 more, okay. So that is this fact, and now I use that to prove this theorem, okay, and I do that in the following way. What I say is, well, if I take so this is a standard trick in algebraic geometry. You want to prove something about an arbitrary variety, you want to prove some open condition, okay, something that is happening on an open set, okay. So for example here I am trying to, what I am trying to show is that I am trying to say that the condition of non-singularity is open because its complement is it's equivalent to saying that the condition of singularity is closed, and I want to say it is non-empty open, okay. So what I have to show is that the set of points where x is non-singular is actually a non-empty open set, okay. So I'm just saying that if I prove that you take a hypersurface, for a hypersurface if you show that the singular points is a proper closed set, then I am done, because if I show for any hypersurface the set of singular points is a proper closed set, then I am saying that there is a open set which consists of good points. But but any variety has an open set which is isomorphic to an open subset of the hypersurface. Therefore it will have good points, because under an isomorphism of varieties local rings are preserved. Okay, since local rings are preserved, this smoothness condition will be preserved. So under an isomorphism of varieties a smooth point will go only to a smooth point. So if you give me any variety, alright, then I know that I know that there is an open subset of that variety which is isomorphic to an open subset of a hypersurface, and I know a open subset of the hypersurface will contain smooth points. If I know that, then I will know that X will contain smooth points. The moment X contains smooth points, this becomes a proper subset, so it becomes a proper closed subset. So this theorem is just to show that every variety contains at least one smooth point. Okay, and I prove this theorem by reducing to the case of a hypersurface, because I know every variety of dimension R is birational to a hypersurface in R+1 dimensional affine space. Okay, so because of this fact, assume that X is assume that the variety X is a hypersurface, right. So now the proof is just probably a few lines. So assume X is a hypersurface in Z of f in AR+1. Okay, what do I have to show? I have to show the singular points of X is a proper subset. Okay, so if let's look at this, let's go by contradiction. If the singular points of X is all of X, okay, then what it means is that dou f by dou xi, okay, vanishes on Z of f for all I from 1 to etc up to R+1. So here now the xi's are all the affine coordinates in R+1 dimensional space, and if the singular points is the whole of X, that means these these components of the gradient of f, okay, they all need to vanish. Okay, a point will be a smooth point if at least one of them does not vanish at that point, but the only way that every point is not smooth, okay, is that all of these guys vanish, alright. But then you see, what does this mean? If, see, after all these are polynomials, and if they vanish on the variety, then they have, then you know that by the Hilbert-Nordström-Sachs they have to be some power of they have to be in the ideal generated by f. Okay, so you see, so by the Nordström-Sachs you see dou f by dou xi, they all belong to the ideal generated by f for every I. That this is because of Nordström-Sachs, which says that if a polynomial vanishes on a variety, then some power of that polynomial should be contained in the ideal of the variety. Okay, so if this vanishes on Z of f, then some power of this is contained in the ideal of f, ideal of Z of f, but ideal of Z of f is just the ideal generated by f. Okay, and if some power of that is contained in f, then that itself has to be contained in f, because f is irreducible and therefore the ideal generated by that is prime, alright. So you will get this, but then what is the degree of f? This is more than the degree of this, will have degree at least 1 less, right, because you have taken a partial derivative, and therefore this condition will tell you that this is these are all identically 0. So this will imply that dou f by dou xi are identically 0 for all I. Okay, it will tell you that all these partial derivatives are identically 0. Now you see if you are in characteristic 0 this cannot happen, okay, because if when will the partial derivatives of all the variables be 0, always will be 0 for a polynomial if those variables do not appear in the polynomial at all, okay. If a variable appears in a polynomial, okay, and if you are in characteristic 0, okay, then that variable will come with a coefficient, alright. So when you take a partial derivative, okay, the coefficient will not kill it because you are in characteristic 0 and the partial derivatives cannot vanish, okay. So the fact that all the partial derivatives vanish, so this implies that characteristic of k is not 0, okay, because in characteristic 0 this cannot happen, and in characteristic, so if characteristic is not 0 then the characteristic of k is positive, is a prime positive, alright, and in positive characteristic if a polynomial is in a certain variable, partial derivative is 0, it means that the polynomial should be a polynomial in the pth power of that variable. So this implies that f is equal to f is polynomial in xi power p for every I. This is a result from characteristic p, and this will tell you that f is g power p, because since your field is algebraically closed, you can take pth roots of all the coefficients and you can use the fact that a plus b plus, I mean if you want a plus b whole power p is a power p plus b power p, okay. So if a polynomial is a polynomial in all these xi power p, okay, then you take the pth root of all the coefficients, then you can write the polynomial itself as g power p, and but this will contradict the fact that f is irreducible, contradicts irreducibility of f. So this contradiction tells you that if x is a hypersurface then the singular points cannot be the whole of x, okay, that means there are smooth points, but already we have seen as a corollary the singular points is a closed set, so that means the complement of this closed set, namely the set of smooth points, is non-empty, okay. So the set of smooth points of a hypersurface is irreducible, non-empty and dense, and since any arbitrary variety is birational to a hypersurface, its singular points will also be only a proper closed set, okay. So that proves that on any variety you have a open dense irreducible subset consisting of smooth points, non-singular points, okay, and the bad points, namely the singular points, they only correspond to a proper closed set, okay. So I will stop here.